Hello and welcome to lesson 7.1 on the angles of polygons. Today we have two main goals, one regarding the interior angles sum theorem and one regarding the exterior angles sum theorem. So we're going to be trying to come up with some sort of general ideas that we can apply to the amount of angle that we expect inside some kind of polygon and how much we expect to be outside. We're going to start with the interior. Start off by reading kind of the introduction here. So a diagonal of a polygon is a segment that connects any two non-consecutive vertices. Okay, non-consecutive meaning you can't connect P and Q because that line would just be the side of this polygon. But if you do the one after Q, okay, P and R are non-consecutive. Consecutive just means one and then the next one. So if we're skipping a vertex and we're going from P to R, then we call this a diagonal. P to S is also a diagonal, right? So there's two possible diagonals that involve P on this particular polygon. The vertices of polygon PQRST that are not consecutive with vertex P and vertex R and S. Okay, that's what we just said. Notice that the diagonals from vertex P separate the polygon into three triangles, right? 1, 2, 3. The sum of the angle measures of a polygon is the sum of the angle measures of the triangles formed by drawing all the possible diagonals from one vertex. Okay, so they're saying generally, if we draw some polygon, so let's go with like a hexagon. And we pick one vertex and we draw out diagonals that reach all the other vertexes, right? The non-consecutive ones. So we're not going to go to that one. We're not going to go to that one. If we draw diagonals out, we end up with a series of triangles. So we're kind of getting into why those triangles were so important to understand in the first place, because other shapes can be broken down into triangles. Okay, so we break it down this way and we have four triangles. Well, any given triangle, we should recall, has 180 degrees on the inside, right? Between these three angles, we will add up to 180 degrees, regardless of, what shape the triangle is. If it's an equilateral with 360s or some other type of triangle, they'll always add up to 180. Okay, so in this one, we have triangle times 4, right? We have 4 of them. So 180 times 4 is going to be 720 degrees. Okay, so for a 6-sided hexagon, we're expecting 720 degrees. Now that is one method for finding what's on the inside. Another method that I've seen also uses triangles, just kind of in a different way. And what they'll do with that is they'll kind of say, okay, go to the middle of your shape and draw lines that connect from each vertex to the middle. In this case, I end up with 6 triangles, right? But if we're trying to figure out how many angles are on the inside of this shape, we don't really want to include those. So if we did 6 times 180, we would get 1,040. Okay, and that would be all of the angles that I'm labeling right now. But we actually wouldn't want those in the center. So then after we do that, we would just subtract 360. Okay. So there's kind of two different ways to approach it. You can either say, I'm going to count up all of the sides. So if I have 6 sides, I'm going to multiply 6 by 180. And then I'm going to take away 360 at the end because I'm going to remove these center ones. Or we can do it in this way, in which case the number of triangles we will make will always be 2 less than the number of sides we have. So if we made a pentagon, okay, 5-sided shape, and I made my triangles by going from one vertex and making the diagonals that are possible, well, I make 3 triangles with a 5-sided shape. Let's test that out with a 7-sided shape. Or let's go to 8. Probably draw that a little better. Okay, so I am predicting that I will make 6 diagonals. And I should, right? Because I'm going out to every corner other than the two I'm right next to. So if there are 8 sides, then I should be going out to 6 of them. Well, sorry, I may have misspoke slightly. There are 8 sides, there are 8 vertexes. I'm starting at one of them, and I'm not going to go to either of these two. So I've got 5 to go out to. When I go out to 5 places, 1, 2, 3, 4, 5, when I make those 5 lines, I end up with 6 triangles, right? 1, 2, 4, 5, 6. Okay. So two different ways, two different like formulas we could make. We can either say it's your number of sides. So -2, like this 8-sided shape, -2, with 6 times 80. Or we can just do n times 180 minus 360. Now these two are the same thing. If I was to distribute over here, well, I would get n times 180, and I would get -2 times 180. Well, -2 times 180 is just minus 360. Okay, so we have the same formula. It's just kind of two different ways to approach it. So the one that I was familiar with originally before looking through the book was this method, but this method works just as well, dividing it into triangles of kind of different shapes and just multiplying 180 degrees times that number of triangles. Okay, so that is the polygon interior angle sum theorem. If we're trying to figure out what is the total of angles on the inside, the sum of the interior angles will always be the number of sides minus 2 times 180. Okay, so if we apply that to a triangle, well, the number of sides is 3 sides. So if we do n minus 2 times 180, for this, our n is 3. We have 3 sides, so 3 minus 2. Well, 3 minus 2 is just 1, so we get 180, like we expect to get. Okay, and that is the formula that we're going to be using when investigating scenarios that have us looking at the inside angles of different polygons. Okay, we will take a look at example 1 in our next video.